I guess let's get started. So I think last time what we are left was I think we covered the weaker generalization bound. And then today we are going to provide a stronger generalization bound for the neural network. Let me just double check whether sorry, I think somehow I got confused where I'm left. Okay, cool, yeah. Okay, yeah. So last time what we did was that we had this generalization bound of the form that you have something in the square root m in the denominator, and today we are going to remove that square root m. Not exactly by just improving the bound. We also have to kind of like somewhat change the hypothesis class. So that's the first part of the lecture, and then we're going to talk about today we're going to talk about stronger. So first we talk about stronger version, and then we talk about some connections to kernel method, and then we will talk about even stronger bound for multiple layer neural networks, and that requires some preparation with some techniques, and we'll talk about those techniques if we have time today. Otherwise, we'll talk about those next week. Okay, so just to briefly review the setup. So the setup was that we have some theta, which consists of 2 layers, and the first layer is I think this is called second layer, which is the vector W, and the first layer is a matrix that maps dimension D to dimension M, and our model is something like W transpose phi of UX, and phi is element-wise ReLU. And so last time, what we had was that we have this generalization bound of the form that this Rademacher complexity of H is bounded by something like 2 times BW, BU times C square root n over n, where H is defined to be something like where you restricted 2 norm of W to be BW, and you restricted the max 2 norm of UI to be BU, and that's the hypothesis class. And in some sense, if you, I guess we discussed this a little bit in the class, so, and also I think somebody asked this question. In some sense, there's a scaling invariance because you can, so alpha times W 1 over alpha U would be the same model as W times U, right? So just because you can scale the first layer by alpha, and then you downscale the second layer by 1 over alpha if alpha is bigger than 0. So that means that you can also kind of change this bound a little bit and rewrite it as something like, basically you can say that, roughly speaking, the generalization error is something like bounded by O of square root n over n, oh, sorry, this is square root n, over square root n times the norm of W times the max I, the max of the 2 norm of U. This is kind of the intuitive way to think about this. So so today we're going to have a stronger bound that doesn't have the square root m here, but we'll have some slightly different terms here in terms of how do you measure the complexity of W and the complexity of E. Okay, so here is a refined bound. Let me state the theorem first. So the theorem is that we define this complex measure that's called C of theta. This complex measure is defined to be the sum of the absolute value Wj times the 2 norm of Uj, and you take a sum over J. And correspondingly, given this complex measure, you can define the corresponding hypothesis class, which is the family of functions with bounded complexity, something like bounded by B. And also we assume that the norm of xi is less than c for every I. Note that here actually we have a stronger assumption of data because before we assume the average of the norm is less than c, or the average of the square norm is less than c squared. Now we assume each data point is less than c. This is just the technicality in some sense. And with all of this, then we can prove that the Rademacher complexity of H is bounded by 2 times B times C over square root n. Okay, so maybe let me first start with some interpretation of this theorem and see why this is an interesting one to prove, and then I'll prove the proof. So a few remarks. The first one is that why this is better than before, right? So I'm claiming that this is strictly better than before, at least in the following sense. So if you really, I guess, so the way that I compare them is the following. So before what we had was that, this generalization is something like square root m over square root n times this complexity is something like 2 norm of w times this, right? As we said. That's kind of the intuitive way of thinking about it. If you assume the c is a constant, c is just something about the data which doesn't really change as you change the hypothesis class. Is really something like a constant. And now you can basically think of this new bound as big O of 1 over square root n times b. What is the capital B? The capital B is basically sum of wj times uj2 norm, right? So basically, the way I'm comparing them is that I'm comparing these two quantities. And I claim that the second quantity is strictly smaller than the first quantity. And the reason is just that if you do some simple inequality, you can see that this is less than, so you first do a Cauchy-Schwarz, you say this is less than sum of wj square half times sum of uj2 norm square to the power half. And then the first term becomes 2 norm of w. And the second term is you can bound each of them by the max. So you get m times max j uj2 norm square a half. So what you got is square root m times w2 norm times max j uj2 norm. So this is in this sense, this is a strictly better a bound. And they could be the same, if your wj and uj makes all of these inequalities exactly equal, but in other cases it won't. And in some sense, you can see one of the intuition here is that this new complex measure. So and another thing is that this new complex measure C theta captures the invariance, captures the scaling invariance better. What do I mean by that? So what I mean is that, what I mentioned the following scaling invariance, right? So if you have W and U, this is equivalent to alpha W 1 over alpha U, right? This is because like the value is scaling invariant and you can do this. But actually you have a little more scaling invariant. You can scale actually each pairs of neurons, in this way. So what you really have is that this is actually equivalent to, you can scale each Wi to something like Wj. You scale each of these the j's coordinate by alpha j, and you scale correspondingly 1 over alpha j times uj. And you do this for different scalar for every wj and uj. And this is still the same, right? Just because, the sum of wj relu uj transpose x is the same as alpha j wj phi of 1 over alpha j uj x for any uj, for any scaling that is positive, right? So, and you can see that if you consider this kind of invariance, still this complex measure is the same, right? So the complex measure is really invariant to the scaling here, because if you change Wj and Uj accordingly, you don't change the complexity, which to some extent, seems to be a good thing to have, right? But before the complex measure doesn't have this property, right? So if you look at this complex measure, if you scale each of the Wj by a different scalar and you scale each of the Uj by a different scalar, you wouldn't, this number would change. Sure. Right. Right. So you are saying that this, okay, yes. So yes. So this one, you do make a stronger assumption. Sorry. Okay. I say by C. Yes. Sorry. What was the question? Maybe I didn't answer. I didn't answer.
I was thinking you write that more like the big option of this EX. Or,
So yeah, but I think I'm guessing what you are saying is that before the condition was something like, I think it's 1/n times sum of xi 2 norm square root is less than c. That was in the previous theorem, I think. Or something like, or maybe that was in the previous theorem we read this. It's less than c squared, right? So indeed this is, so the new condition is stronger than the old one, because this one implies the old one, right? So yeah, so I'm assuming that suppose you say this is not a problem, like you just live with the stronger assumption, then our bound is strictly better. In some sense, this assumption of x is a little bit less important to some extent, because for example, if anyway our data satisfies the stronger assumption, then it's less important, right? So yeah, but you are right that the data assumption is a little bit different, but I don't think it matters that much. Right. That's true. That's definitely true. Or you can choose the right C. But I think the question was more about comparing the two theorems. If you normalize here, maybe you should normalize there. So what's the fair comparison? Cool. So this is one other thing about this complex measure. In some sense, like this complex measure is a little bit more invariant to at least the trivial invariance in the network. So and also the bound is better. And also another thing that we have about another thing about this is that about this theorem is that if you have m goes to infinity, at least you get a stronger or equally or a stronger or equivalent theorem. So the theorem is stronger. So what do I mean by that? So let me explain this. So suppose you look at a dependency on m, right? So this whole theorem depends on m implicitly somewhere. I didn't specify that, but now let's make it more explicit. Let's say hm is this complexity and the same thing, right? So where you have m neurons, and also c theta is less than b. All right. So for every m, our theorem applies. So, but I'm just making dependency on m a little bit more explicit. And you know that hm is a subset of hm plus 1. In what sense? In the sense that, if you have a function that is in hm, you can always, add a fake neuron, a zero dummy neuron, to make it in hm plus 1, right? Just so any f theta in hm, you can add a dummy neuron. So meaning that you make w plus 1 0 and the u m plus 1 0, and then you can extend this function so that it becomes in hm plus 1. So hm plus 1 is always it's a bigger family of functions than hm. So that's why you have a strong, but the bond doesn't depend on M, right? Like you have the same Rademacher complexity for every M. So in some sense, your bond would be stronger for bigger M. So the strongest theorem would be you just apply it for H infinity. So and that's actually in some sense the fundamental reason why later you'll see that you're gonna have a generalization bound, at least a generalization bound that is decreasing as M goes to infinity. So and that's another nice property of this complex measure. And also another small remark is that there's something called parse norm. If you haven't heard of it, probably doesn't matter. This is a complex measure that people empirically that people proposed, and people evaluate that. People found that this is correlated with the real generalization bound empirically, and this is very closely related to the definition of C theta here. So in some sense, what you kind of see, kind of the parse norm is trying to say that you look at all the paths from the input to the output, and you look at the total kind of norms of all the paths. And in some sense, this is kind of like that. It's not exactly the same depending on which version of the parse norm, but kind of like the way you think about this is that you look at the input X, and so this is Wj, and this thing is Uj. So in some sense, you look at so every parse matters, right? So that's why you look at Wj times Uj first, and then you take the sum. Instead of you look at each layer first, and then you multiply. Yeah, if you haven't heard of the parse norm, what I said probably wouldn't make that much sense. Like, but if you have heard of it, probably you can see the connection. This is not super important. This is just something people have empirically studied. All right. So we'll talk about more implications of the theorem later. But before that, let me prove it. Any questions so far? Okay. So how do we prove this? So you can see that the kind of one of the main point in the proof is that you want to kind of like change the scaling in the right way, because you want to capture the scaling invariance. You don't want to peel off. So before, what we did was that we tried to remove the W first, and then we remove the U, right? You have a soup over W and U. You somehow remove each of them sequentially. And now the thing is that you still do the same thing, but you want to remove them sequentially as well, but you want to first rescale things first and then remove them so that you can eventually get the right kind of scaling environment. I'm not sure whether this makes sense. Like you see like more clearly in the proof. So first of all, let's define this vector U. Let's define U bar to be the normalized version of U. So and then let's start with the derivation. So what we have is that the Rademacher complexity is something like this. I put one over in front just to make it easier. So you have, this is the definition. And I guess we do the usual thing. The first two steps are just plugging in the definition. And now we want to first rescale W and U before we take the soup. So what we do is that we write this as Wj Uj2 norm. So and then we inside the phi we use Uj bar transpose Xi. Right. So in some sense you put a norm of Uj outside of the phi. The norm of Uj is a positive number, so you can put it outside of the phi. And sorry, I have a little bit trouble reading this, but I think I can remember what. Oh, okay. like there's a page segment so that I couldn't read what my notes were. Anyway, so you rearrange this a little bit. So in some sense, we treat this wj times uj2 norm as our old wj, and we want to kind of remove that first. That's kind of, and also you can see that this one is something that shows up in the complexity measure. The complex measure is basically the sum of this is less than b, right? The complex measure is really just the sum of wj uj2 norm, right? So you have sup over theta, and you, I guess, rewrite this. You change this, the order of the summation, so that it's clearer that you have this times from 1 to n uj phi of uj bar transpose xi. And here, I guess let's specify what the constraint of theta is. The constraint of theta is that c theta is less than b, which means that this wj uj2 norm is less than b, right? So the constraint is really just saying that the sum of wj uj2 is less than b. And now you can see that the sum of these quantities is less than b, but we care about the weighted sum, right? So we weight each of the quantities by something, and then you take the sum.
Where's the sigma dropped out of that last line? Where is it?
Oh, sorry, my bad. Yeah, there's a sigma here. Sorry. This is the bad. This is the problem when you derive things on the fly. Just this particular line I couldn't read it from my notes, so I'm improvising. Okay, thanks. So and then let's okay. So we know that the sum of wj uj2 is less than b. So that means that you can use an inequality here. So you say that you. So you. I guess maybe let me just have so this is like basically you are applying this. AI BI is less than, you know, the sum in AI times the max of BI. This is what we are applying. Actually, I probably should use J just to be more consistent with. So this is J from 1 to M, and this is J from 1 to M, AJ, BJ. And AJ corresponds to WJ, UJ, 2 norm, and BJ corresponds to this quantity. Right, that's abstractly what I'm doing. So if you live in this, then you get basically the sum of AJ, the sum of WJ, UJ 2 norm, J from 1 to M, times the max over J right. So in some sense, this is a Hölder inequality, right? So like the inner product of A and B is less than the 1 norm of A and the infinite norm of B. And then this quantity, now we got, this is separate quantity, this is less than B, right? So then this is less than 1 over n times sigma times B times sup over theta max J sum of sigma I phi uj bar transpose xi. And now this, if you carefully compare this with what we had before, this should look somewhat familiar, because in some sense we achieve almost the same thing as we have done before. We remove the influence of W, and we only have something about U. And here, what you have about U doesn't have the scale anymore. You only have uj bar. So basically now, what you can do is that you can say that. So from here is basically the same thing as the previous proof. Let me try to repeat a few steps. So I guess one thing you can do is that you realize that this max over J is not doing really much. So what you can do is that you can replace this by max over U bar, where the norm of U bar is 1, and some sigma I phi U bar transpose xi. So that's one thing we can do. Sure. That's good point. So I should have value. So I think I should have it here, and I should have it here, and I still should have it here. Thanks. Yeah, thanks for catching all of these issues. So, and then this, I guess you probably also remember there's a step I skipped before where I removed the F's value by paying a factor 2. So you can do, this is less than this soup. Right, and there was all of these are almost the same as, it's exactly the same as before, and now you can you can remove the phi by the Lipschitz compensation lemma or the Telegram lemma. So you can get rid of the phi. So this is Telegram lemma, and then you can then this becomes the complexity of the linear model, and you do some thing, and then you can get the same thing like 2b c over square root 2, where the c comes from the norm of the xi. Right. So yeah, so basically from after here, these are, so this part the same as before. I guess there's a small difference, which is that the u bar now is normalized to norm 1, right? So you just have so that's why you don't catch up. So before, like if you look at the proof before, what happens is that you don't have you have some other control of u bar, you control of the u. You know the norm of u is less than bu, and now you know the norm of u bar is less than 1. So that's why you don't have the bu show up in the final bound, because the norm of u bar is less than 1. So in some sense, this is just almost the same proof, which the only difference is that you somehow remove the scaling of u first. You put the scaling of u actively in the w, so that you can organize this a little bit better. Any questions? Cool. Great. So I think next, let me talk about some of the kind of like the implications of the theory here. Some of them are kind of like interesting. So I think one thing is that if you believe in the theory, then what theoretically we should do is that this is not what people do in practice, but I would argue this is also close to what people do in the practice. But if you just believe in a theory, what you probably would do is you want to define the following max margin solution, right? You want to do the max margin on the minimum norm solution. So I guess you can do maybe either do program 1, where you minimize the complexity of c theta, and with the constraint that the margin is larger than 1, right? Why we care about the margin, recall that all of this depends on the margin eventually, because eventually your generalization error will be the complexity over the margin. Or alternatively, I think these are exactly equivalent. So you can say that you maximize the margin, and with the constraint that your complexity is less than 1. So let's call this program 2, and we can probably define this to be gamma m star. I guess I probably don't have to define now. So you can do this 2 program, right? So, and this 2 program, the reason why you want this program is because your generalization error bound will be something like, the generalization error will be something like L theta will be less than L theta hat will be less than C theta hat over gamma min theta hat over square root 10 plus low order terms. right? This is the using the general machinery that we had, right? So you have 1 over square root 10. So like you basically have the Rademacher complexity. This is the Rademacher complexity. And sorry, I mean, this part is the Rademacher complexity. This corresponds to the Rademacher complexity of H, and this is the margin. Right, so that's what we got from the margin theory.
Is there anything deep difference between the ground and matter and this one? Like, it just seems like you kind of coded in this way and then it's easy to see. So, is there something you could in this way?
I think depending on, I think you are basically right. But I think I would say this is already something, like we already achieved something, because this, I think maybe the right way to think about this is that you compare these two things, right? So in the very idealistic way, right? So for all the WJs are the same, all the UJs are the same, then these two bonds are just the same. So then you are right. You are just folding, you are just changing your form of your bond and nothing really changed, right? You somehow fold the square root m somewhere. But the thing is that this is not tight always. And you probably shouldn't expect it to be tight. It shouldn't be the case that all the WJs and UJs are the same. You probably should have a decaying WJ. As you have more and more neurons, you're gonna have smaller and smaller WJ. Just be, like there's no way that this is tight for all M, right? So like it can be tight for for one M, but if you add more neurons, it wouldn't be tight. So the typical thing would be that you have more, as you have more and more neurons, these neurons probably should have smaller and smaller norm, because they are capturing like more and more kind of complex subtleties in your function, in your ground truth function, right? So basically I'm saying that this inequality wouldn't be tight in the idealistic in the ground truth function, for example. Right. So yeah, but from a very technical point of view, I think that's the only, we only did a very small trick to change the form. Yeah.
So this bound basically assumes that your output would be bound, but the other bound somehow says that your output would be like scale or
Yeah, I think you can say that in some sense, yes. Yeah. Or at least the other bound would be, yeah, I guess depending on how you think about it, yeah. But I think the way I think about this is really just okay. The way I think about it is that these two bonds are exactly the same when all the WJs and UJs are the same, like they are all, for example, constant or something like that, or maybe all 1 over square root m. So then you don't gain anything from this, right? So, but it will be much different if you want to find the function where your WJ and UJ goes to 0 gradually as you have more and more neurons. Okay, so right. Okay, so going back to the generalization bound. So I think the generalization bound in some sense motivates the use of this kind of like max margin solution or the minimum norm solution, just because eventually your Rademacher complexity depends on the complexity of the model, and you also have the margin term from the margin part, from the loss part. So, and one of the interesting thing is that this quantity, if you think about this quantity, and this quantity you can show this is not increasing as m goes to infinity. So and the reason is actually pretty simple. So, but maybe let me write it down just to be clear about what I really mean. So let's you say that hat m to be the minimizer of say program 1. Right. So and m is to index how many neurons you are using. So for every m you have a minimizer, and you can define gamma m star to be the solution of to be the corresponding margin, right? You can define gamma m star to be the margin with the constraints that d theta less than m. So let's say define this to be gamma m star. Right. So I think I want to define this to be 2. So let's mostly use 2 as our main thing. Like this is a little bit typo here. Okay, so so suppose you solve this program 2 and you get this max Martin solution, right? So and then so your bound, so this means that the bound is c theta hat m over gamma mean theta hat m over square root n, and because we normalize the complexity to be 1, so this is really 1 over gamma m star times square root, right? This is the generalization bound. So basically, whether this bound is better or not depends on whether gamma m star is increasing or decreasing. And interestingly, the gamma m star is increasing. This is and this is in some sense almost by definition. Why? This is because if you think about what the gamma star m star means, it means that the maximum margin you can achieve when you restrict your complexity to be less than 1, right? And also use m neurons. And the thing is that when you have more neurons, at least you would achieve the same margin. You shouldn't be worse. Just because the only right, so with more neurons, you never get worse. Can at least achieve the same margin by adding just the dummy neuron as kind of exactly the same argument as I had, right? Can at least achieve the same margin. Because you just add a dummy neuron and it doesn't change the functionality, it doesn't change the complexity, it doesn't change the margin. It just everything is the same. But having more neurons give you additional flexibility. You could possibly kind of change your neurons a little bit more cleverly instead of just adding a dummy neuron. That's why your margin, adding 1 more neuron will potentially make your margin bigger. So at least you never get the margin smaller by adding neurons. So that means that this bound can decrease as m goes to infinity. At least it's not increasing as m goes to infinity. So in some sense, this is kind of the nice thing about this compared to other bounds where you have explicit dependency on m. If you have an explicit dependency on m, at least if you just look at it, you wouldn't be able to argue that this bound is better. So now you can say this bound is better as m goes to infinity. Of course, this doesn't really say, this doesn't address everything because this is just the upper bound, right? It's not like you are saying that the actual generalization error is decreasing as m goes to infinity. That would be the ideal theorem you want to prove, right? That would match exactly the plots I showed last time, where you have more neurons and your accuracy is improving or your error is decreasing, right? So here you're only talking about bounds, right? So if the bound is loose, then it's unclear whether this decreasing in m thing is really a big deal. And that's indeed true. So, but I think this is in some sense, this is a starting point, right? So if your bound is increasing in m, that is completely useless, right? Your bound is decreasing m, that doesn't really mean that it's super powerful, but at least that's a good sign to have, right? That's a good thing to have. Right? And in some sense, it's really hard to capture the exact test error. So if you really want to say that the exact test error or the generalization error is decreasing in m, that's basically the only thing you can do is with linear model. At least so far, the only techniques I know is that you just literally compute exactly what the test error is on linear model. You can do the analytical derivation using linear algebra to simplify them, and in certain cases, you can show indeed the error is decreasing as m goes to infinity. This is actually a pretty popular direction in the last few years. Like people have done this for various kind of linear models, but basically only restricted to linear models. Right. So here we want to work with neural networks, so we have to kind of somehow live with the weaker result. You only say that the bound is decreasing, but not the actual error is decreasing. Okay, so I guess the next thing I want to say is that is actually, okay, another thing that this is different from this program 1 or 2, they are still different from what you do in practice, right? You probably don't do exactly this complexity measure. Nobody regularizes it like that. You know, probably somebody tried. It probably wouldn't make a difference. Here, what I'm going to say is that actually it's interesting that this complex measure is definitely different from L2 complex measure, right? But once you minimize the complex measure, it's you get the same effect as minimizing the L2. Like, or minimizing the L2 is the same as minimizing this. Maybe let me just clarify what does that mean. So basically, my main point here is that if you maximize margin, can be done by minimizing the cross entropy loss. It's the one that with L2 regularization. So here I have two things. One is I'm using cross entropy loss, and the other is I'm using L2 regularization. I'll do one of them as that. So the first, I'm going to first use L2 regularization instead of the complex measure I defined. And I'm going to say that it's actually doing the same thing. So here's the first lemma. So suppose you consider the one we have considered, right? So let's call this J1, which is you minimize the complexity with the constraint that the margin is larger than 1. By the way, I keep changing sometimes I'm minimizing the complexity with the margin larger than 1. Sometimes I'm minimizing the margin with the complexity less than 1. Somehow, yeah, I probably should make them all consistent, but just in my mind, they are always the same. So sometimes I forgot to, sorry, I should probably just keep a single version of it. But they are the same. They are just like equivalent because, yeah. So anyway, so here I'm minimizing the complexity with the margins larger than 1. And I'm claiming that if you look at another one, which is you minimize the L2 thing, the L2 norm, and with the constraint that the margin is larger than 1. So these two are the same. So obviously, these two functions are not the same, right? These two complex measures are not the same. But if you minimize the complexity, the extremal point actually turns out to be the same, which is kind of interesting. And the proof is like follows. So I think at least one thing you know is that the L2 regularization, what is that? This is L2 regularization is the sum of the squares of all the parameters, which is sum of wj squared plus sum of uj2norm squared. And you can show that this is larger than the complex measure we have defined because you can use the AMGM. So you can say this is wj squared plus uj2norm squared, and you use, I think this is called AMGM inequality. Or, for me, everything is Cauchy-Schwarz or JC inequality. So, but anyway, so you get wj times uj2 norm times 2, and you cancel these 2. So this is b theta, right? So you are minimizing. So in J2, the program J2, you are minimizing a larger complexity measure. But I guess the intuition is that even though you are minimizing a larger complex measure, but when you the extremal point actually will make these two things the same. So the intuition is that the extremal point should satisfy wj is equals to uj, even when you are minimizing the L2 regularization, right? So, and if suppose that's the case, then you can kind of believe that these two things are the same, because when I'm minimizing the L2 regularization, if the extremal point satisfies this, then for this case, if this is true, then C theta is the same as the L2. So then you're not really doing anything different. So that's kind of the intuition. If you really want to prove this kind of formally, I guess the simplest way to prove this is the following. So so you say that, I guess this implies that J2 is larger than J1, and you want to use intuition to show that J1 is bigger than J2 instead, is larger than J2 as well. So what we do is that we say let theta be the minimizer of 1 of J1. Maybe let's call this, I think let's call this maybe 3, and this is 4. So is that a good number? That's probably not a good number. Let's call this P1 and P2. So minimizer of P1. And then what you do is you construct, so you get a theta that is the minimizer of the first one. And you want to construct a theta prime, which is very good on the in terms of the second program. So you construct a theta prime, and what you do is that you say, I'm going to take Wj prime to be the renormalized version of Wj, and Uj prime again to be the renormalized version of Uj. And then you can verify that because I'm just changing the scaling, Uj times phi of Wj transpose x is the same as, sorry, Wj times phi of Uj transpose x is the same as before. And also Wj, in terms of the complex measure, they're also the same after doing this transformation. Okay, and this means that C theta is the same as C theta prime, and F theta is the same as F theta prime. So the functionality and the complex measure didn't change. And what's interesting is that for theta prime, C theta prime is also equals to the L2 norm because my construction, okay, why I'm doing this construction? I'm doing this construction because I wanted Wj it to be equals to the norm of Uj. This is why I choose this scaling. By the way, I think this should be like this. Oh, sorry. No. Wait, am I right? Oh, no, it's like this. All right, so you can verify Wj is the same as the Uj this, right? So because this is actually my design in some sense. Like you can verify this, like but this is like if this is true, I should change my design to make it true. But that's the point. So so that means that. So what does this mean? This means that theta prime satisfies constraint of. So all of this means that theta prime constraints of P2. So that means that C theta prime is less than is bigger than J2, right? And C theta prime is equals to, and C theta prime is equals to a half theta prime square is equals to a half. Sorry, C theta prime is equals to. Okay, what is this equals to? This is equals to. Let me see what's going on here. I want to show that C theta prime is equals to J1. This is because right. This is just because T theta prime is equals to C theta, which is equals to J1. Okay, I didn't change the complex measure because I'm just rescaling. So that's why J1 is bigger than J2. And before you get J2 is bigger than J1, so that's why J2 and J1 are the same. Yeah, actually I was a little hesitated. I was a little bit hesitating whether I should show this proof or a more intuitive, another version, which is actually in the lecture notes. In the lecture notes, there's a slightly different way to prove the same thing. At the end of the day, everything is relatively simple. It's nothing really hard. So this proof is very easy to verify, and the other proof is kind of like, in some sense, carries the intuition. The intuition is really just what I said. At the extreme point, this underweight WJ and UJ2 norm has to be the same. So these two complex measures are not different. So that's the main intuition. Say the prime satisfies the constraint P2. So the constraint is only about the margin, right? So the margin is only about the functionality of this model, right? So if you predict the same thing, your margin will be the same, right? So theta prime and theta have the same functionality because you only rebalance the scale, right? You just multiply Wj by something and divide Uj by something else. So the functionality is maintained. So that's why the margin is the same.
In the first line of the proof, why is there inequality?
In the why there is no.
First line of the proof when we pull out the sum.
Here.
What we did.
Yep. So here, this is the equality.
The line below it.
Oh, sorry. This, my bad. Why? This is equality and this is inequality. My bad. Okay, cool. Okay, great. So the first thing, so the first lemma we have shown, what we have done, we basically are saying that if you minimize the L2 norm, it's the same as minimizing this complex measure. Okay, and we also wanted to do the cross entropy, and this is something I'm not going to prove, but I'm just going to state a lemma, and if you're interested, you can read a paper about it. Like, the proof is actually relatively simple, but I think we'll probably have time today to do that. So the lemma 2 is that if you consider a regularized cross entropy loss, and something like L hat lambda theta, which is equals to 1 over n times, I guess in this lecture, this is the first time I have ever talked about what cross entropy loss, but I assume that you somewhat know what they are, right? This is the loss for logistic regression, right? You have yi times f theta xi. So this is the input, and the loss is the log of 1. So the loss in some sense is really log 1 plus exponential minus t. This is the logistic loss. And you add some lambda times the L2 regularization. Suppose you do this, and let's say let theta lambda hat be the minimizer. I'm going to claim that for small enough lambda, theta hat lambda is basically doing the same thing as the max margin solution. But there is a small thing that I have to deal with, which is that what is the norm, right? Because the max margin thing is you need a norm. Basically you need to care about the ratio between the margin and the norm. So that's why my statement is that again, I don't know why. Okay, yeah. So then, so my statement is something about this. It's like this. So basically, you can say that if lambda goes to 0 for small enough lambda, then the norm versus the margin will goes to J1, which was defined to be the minimum norm solution, right? This is just I'm recalling the definition. So basically, you are converging to the max margin solution or the minimum norm solution up to a scaling, because here I'm looking at the ratio. So this when you have a very small theta, when you have this very small lambda, your norm of theta would be something actually pretty big. It's because your regularization is too weak, so you are going to get very big norm solution. But if you normalize the norm with the margin, then you found that this is actually the max margin solution. I'm not going to prove this. I guess if you're interested, this is a theorem 4.2 of a paper I wrote with some collaborators. And actually, this theorem is actually very simple. Like, and actually, it works for not only the L2 regularization, it works for almost all homogeneous, or like almost all regularizations you can think of. So the gist is basically saying that if you care about the max margin solution with respect to certain complex measure, right? So like the complex measure could be L2. In this case, it could be something else. Like here, it could be anything, right? So one way to achieve it is that you just add a very weak regularization in the cross entropy loss, and that will give you the max margin solution. Okay. Any questions?
We have that point at the general result.
Yeah. Yeah. So the general kind of like the gist is that suppose you care about the max margin solution, right? But max margin solution requires a complex measure, right? You need to say I'm minimizing the norm, such a norm with the margins larger than 1, or I'm maximizing the margin with some constraint, right? There's a norm, right? So there's a complex measure. So if you want to get that max margin solution, you just put a complex measure in the here, right? So and with a small enough lambda, then and then you have cross entropy loss, and then the solution, this will give you the max margin solution. Of course, you can look for the max margin solution, just directly by solving the program, but you can also do it like this way. And this is something that seems to be more typical. Like at least this is what people do empirically all the time in some sense, right? In some sense, this is just linking what people do empirically with the max margin solution, which is not what people do that typically in deep learning. Right. But there is but the caveat here, like if you care about the broader interpretation, the caveat here is you need the lambda to be very small. So basically, this is saying that if you use a very small lambda, you get a max margin solution. But empirically, actually, you don't use that small lambda. You actually use something bigger than this infinitesimal small lambda. So empirically, you probably wouldn't get exactly max margin solution. You're going to get something similar to it, but not exactly the same. And actually, it's kind of interesting that, like I guess probably for CS229, like you have learned like the max margin solution, right? So it sounds like before deep learning, that's the right thing to do, right? Like, but even you look at linear models, it's never, at least I haven't seen. I'm not a practitioner. I do a lot of theory, but when I do experiments, I've never seen that max margin solution is the best for linear model. Somehow. It's like when you use a very small lambda, you do get max margin solution, but if you use bigger lambda, sometimes it's a little better. So I think max margin solution in some sense is just a theoretic approximation of what people really do in practice. All right, so let me see. So the next part, I'm trying to connect this deep learning thing, this deep learning, not very deep, like two-layer network thing with the so-called L1 SVM. This is also a kind of like I think people like the exact kind of like thing is in my paper as well, but it's only like 3 paragraphs in appendix, and we are not really inventing it. We just in some sense said something that people already knew. Implicitly, we thought that it's useful to write it down. So the general thing is that you want to say what we want to claim is the following. So we want to claim that this is really doing what neural network is doing with this two-layer network and the max margin solution. It's really just doing something like L1 SVM in some kind of feature space. So, but let me explain, I guess I haven't defined what L1 SVM is, right? So you're probably familiar with SVM. That's the so-called L2 version of the SVM. So here you are going to have a slightly different version of SVM. So the idea is that first of all, let's look at infinite number of neurons, because we have claimed that more neurons is always better. So why not think about infinite number of neurons? And let's see what infinite number of neurons it will do for us, right? So you look at the max margin when you have infinite number of neurons. This is the largest possible margin you can achieve with even infinite number of neurons. And suppose that this is achieved by U1, so on and so forth. You need infinite number of neurons, probably. So many neurons. Actually, you can achieve this without infinite number of neurons. You can achieve it with, I think, n+1 neurons. N is the number of data points. So, but let's say you have infinite number of neurons. Just like basically, infinite is not very different from n+1 neurons. As long as you have more than n+1 neurons, you don't really gain anything more from this. So, and let's again, U bar is the normalization of U. So I think we have kind of played with this like a lot of times, right? This is equivalent to W1, U1 2 norm, U1 bar, so on and so forth, right? This is what we have. Let's call this theta. I think I call it theta tilde in this case, and I call this one W1 tilde. Okay, so we have kind of like done this rescaling a lot of times, and we know that if you rescale this, you don't change the complex measure, and here the complex measure is right the WJ UJ2 norm, and this is just the WJ tilde absolute value. So this is the one norm of WJ W tilde. So that's where the one norm comes into play. So basically, the idea is that after you change this viewpoint, basically you just view W1 tilde as the variable, and then you are doing some kind of like sparse linear regression or sparse SVM. So so formally, what you can do is that you can say you can pretend so every U in the sphere on the sphere SD-1 is the d-dimensional sphere. So you pretend every U in the sphere shows up in the collection of U bars. Right? Once you pretend that every U, and why this is possible? This is just because adding more neurons is never a bad thing. Right? You add a lot of neurons to the UIs, and you just set those corresponding. This is just because you can add neurons, add UJ and 0, right? You just add these things. It never change anything, right? If you don't see any neurons in this collection, you just add this neuron into the collection, and you add 0 as the coefficient. It doesn't change the functionality. It doesn't change the complex measure. So that's why you can pretend that the collection of U1 up to UM, and I guess there's also more, you have infinite of this. It's really just a collection of all the possible unit norm vector on the sphere. Right? That doesn't really change anything. And once you have that, then, so once you pretend that this UJ bar is just equals to SD-1, then you can take a continuous perspective. You can say that this F theta tilde X it's really something like sum of, right? If you write the discrete version, you get this, but you can say this is, you can think of this as a continuous version, where for every U bar you have a W, and you are integrating over all the U bar. I'm not sure whether this makes any sense. This is the simplest way that I came up with to define this without talking about what's of. At least, this is one way that I came up to explain this without too much jargon. But of course, I don't know whether this works for everyone. Again, in the lecture notes, there's a slightly different way to introduce this, which requires a little bit more jargon. I don't know. Any questions?
What's the sigma?
Oh, sorry. Wait, my bad. Why am I writing sigma here? Phi. Yeah. Sorry. Okay. Yeah, feel free.
Can we have an uncountable number of neurons?
Right. Okay. Yeah. Can we have uncountable? So the question is whether we can have uncountable number of neurons. Here, this is not super like. This is just a concept, like for example, the same question you could ask the same question about why you can, when you define the integral, actually you are using the countable number of discretizations, and you take the limit, you can still get something uncountable. So this is kind of the same thing. It's yeah, and also in some sense, eventually this thing is kind of like just a language in some sense. It's not really like you implement the integral in practice. So yeah, does it make some sense? Okay. So and basically, I think if you see this is kind of like what you can, the way you can view this is that you can say this is a W tilde inner product with a phi, and the phi X is a universal feature map. So basically, you think of this, each of this is a feature. This is a feature, and this is like the coefficient in front of the feature, and this feature is now the feature is the difference between now. The difference here is that this feature is a predefined feature. It's no longer something learned, because you have all the possible U bar in this world in your feature set. So basically, you can view this phi X is really just this gigantic feature. Okay, phi feature vector where you have all the possible U bars in your feature set. So and W tilde is the coefficient in front of feature. So basically, if you kind of like take CS229, then this is the feature in the kernel part, and this is the theta or the weight vector or the parameters in front of feature. So now it's a linear function in the feature in the features. So but the thing is that the complex dimension corresponds to, as we argued, corresponds to W tilde 1 norm, but not 2 norm. So this is why the max margin with this phi theta is less than 1 corresponds to max margin with this L1 norm max margin. So basically, you can think of this as the corresponding questions. You are maximizing the margin. The margin is the same, so W tilde phi xi. Take the mean over I, and max over W tilde, and with the constraint that the 1 norm is less than 1. And this is called L1 SVM with feature phi. So and the difference from the SVM you learned in the, for example, CS229 would be that this is 1 norm but not 2 norm. So it's not doing just a simple kernel SVM. It's doing something different from that. And the interesting thing is that the L1 SVM is actually not implementable with infinite number of features. It's not implementable. So like when you take a CS229, one of the messages we had is that when you use the kernel trick, you can actually work with infinite dimensional feature, because you can change everything depends on the kernel, the inner product of the features. So you don't really care about dimensionality of the features. So you can work with infinite dimensional feature. But here you don't have that kernel trick anymore. So if you have the L1 constraint, the kernel trick doesn't apply. The final solution is not just a function of the inner product of the features. So you cannot apply the kernel trick. So that's why you cannot implement it with the with the kernel trick. So this part is purely for understanding. This is saying that okay, neural network is doing something more than what you can do with kernel, because now you are effectively doing a L1 version of the kernel problem, which was not able to do, which is something you are not able to do with the standard kernel trick. You have to use the neural network to achieve the same thing.
So did we prove that L1 SVM is not implementable, or is that just sort of a
we didn't prove that L1 SVM is not implementable. But I think how do I say this? I guess, how do you prove that it's not implementable? Like you have to say what does it mean by implementation. So this is just really we don't know. Maybe the easiest way to say is just we don't know how to implement it, but it sounds like very unlikely to be able to be done. Also on the other side, on the flip side, for neural networks, right, we are saying that you can implement it, right? You can so basically here is saying that you can effectively use neural network to implement this L1 SVM, but the caveat is that you still don't know whether you can optimize the network. So it's not an end-to-end result. It's saying that if you assume you can optimize your network efficiently and up to global minimum, then you can solve the L1 SVM. But there is a caveat about whether you can really computationally solve your neural network. That's something we don't know how to do. Like we don't know how to prove theoretically. Empirically, it sounds like true. You can do it just by gradient descent. Okay, so I think this is all I wanted to say about the two-layer network. Next, we are going to talk about, our next goal would be to prove something about multiple layer network, and we need more tools. So my plan is to spend the next 10 minutes to talk about some of the tools, and we need to continue about the tools in the next lecture, and then we can talk about how to have better bounds for multi-layer network. But if there's any questions, I can talk about that. I can answer any questions first. It's a little bit awkward. I think I thought I have 20 minutes, but there's only 10 minutes. But still, I think it's okay. We can start with the simple thing. But this will be a kind of like at least for the moment, it will be a quite different mindset. We are thinking about the tools again. Okay, so now we are getting back to how do we bound the Rademacher complexity. And we are talking about a different type of tools. And let's recall, maybe, okay, I guess before doing that, maybe let's think about a function space view of the Rademacher complexity. So maybe let me write down the Rademacher complexity first. So this is something like, if you have a function class f, the Rademacher complexity is, this is the empirical Rademacher complexity. Right. So if f as is equals to z1 up to zn. And let's think about, let's define the following set Q. This is a set of vectors, and the vectors are the outputs of f on these endpoints. So for every function, you're going to have a vector, n-dimensional vector. And So this is basically the set of outputs of f on the data points z1 up to zn. Right? These are all the possible outputs you can get from applying f on this set of points, and they are vectors. And then you can rewrite this as the Rademacher complexity as the following. So you can think of this as you are looking at all the possible vectors v in Q, and you look at the inner product of sigma with v, right? Just because this 1/n sigma v is really just the sum of sigma I vi, which is the sum of sigma I f zi. This is just rewriting. So the point here is that this RSF only depends on Q, depends on the outputs. But for example, but not as opposed to the, for example, the parametrization of f. Let's make sense what I mean here. So for example, let's say suppose you have a function of class f, which is f of x is equals to something like sum of theta I xi, where theta is in dimension d. And suppose you have another function class f prime, which is of the following form, say something like sum of theta I, I'm writing something, where theta is in d and w also is parameter in d. This is just a weird example just to demonstrate a point. So suppose you have these two function class, and they have different parameterization, they have different parameter space even, right? So one has d-dimensional parameter space and the other has 2d-dimensional parameter space. But these two functions have the same Q, corresponding Q, because they're the family of outputs are the same. Because in some sense, you can have a one-to-one map between a function in capital F and a function in capital F prime, because they are just like for every possible outputs that can be output by the function f, you can also find the one that can be output by some function in f prime. So they have this different parameterization, but they have the same functionality in some sense, or it's the same family of functions. And they have the same Q, and then that means they have the same Rademacher complexity. So I guess I'm just trying to reinforce this idea that the only thing that matters is the outputs of the functions, but not how the functions are represented or parameterized. And this would be useful kind of like as a general thing. It's kind of like a change of mindset, right? So before you are talking about the parameters, right? So what are the parameters of f? How do you discretize your parameters? From now on, we are not going to think about the parameters that much. We are more thinking about the outputs of the functions. And there's a so-called Massa lemma, which is actually one of the things you are asked to prove in the homework. So this lemma is saying that if this Q, right, satisfies that Q is, first of all, so I guess maybe let's say for every vector v in Q, the 2 norm of v over square root n is less than m. So this set of Q contains only bounded vectors in this sense. By the way, from now on we're going to see these things very often, just because you want to normalize your vector. You measure the vector by the normalized norm. So norm itself doesn't matter that much. You want to normalize the norm by the dimension of the vector. Right. Right, that's right. But I think this is actually a very good question, which I probably should have talked about early. So I think probably I mentioned this a little bit at some point. So one of the nice thing about empirical Rademacher complexity is that now you are in this mindset that your zi's are fixed. So you don't have any randomness in zi's. They are just the endpoints fixed there like forever. And of course the functions can be changed, right? You have a family of functions, but you don't have a changing zi's. So that simplifies things a lot in some sense. And so in some sense you can think of this, even in some sense, like you can think of the functions, the family of functions are functions that map zi's to real numbers, but not functions that maps like RD to real numbers. Like you can forget about any other points. This will just have endpoints, and all your functions can be just represented as n numbers, right? Which are the outputs on these endpoints. There's no any other points you have to care about. That's kind of the beauty of the Rademacher complexity in some sense. Like that's kind of the why it's powerful, because before the z is the source of the randomness, but now the randomness comes from the sigma. So that's why you can fix zi's.
So is this going to be a statement about if you have like, as long as you have more than, for example, 10 degrees of freedom in the zone matrix, that you can have the same.
As long as
you have greater than equal to 10 degrees of freedom, because then you can like maybe have all possible assignments.
I think you're the exact thing probably is not what like Guido said, but you are on the right in the right direction. So basically the Rademacher complexity depends on how complex this set Q is. That's what we're gonna say. And actually the next lemma you can see that this, like I think we have actually mentioned this before. So if Q is not very complex, for example, if Q is a finite set, then you have a good Rademacher complexity. And of course, how do you measure the complexity of Q? That's a little kind of like it's a question that we have to study. But there are, for example, if the Q is finite, then you have a bound on Rademacher complexity. That's what I'm going to write. So suppose, you need two things. One is that Q is finite, and the other thing is that Q is kind of like roughly bounded. And these two things, then you have that this expectation over sigma of this thing, which is equivalent to Rademacher complexity, is bounded by square root 2m squared log Q over n. So the size of Q come into play. And I guess as a corollary, I think this corollary is something I have presented before without a proof. If f satisfies that this function is bounded on this zi's in the following sense: the average output is bounded by m squared, the average output square is bounded by m squared, then the Rademacher complexity of f is bounded by 2m squared log f over n. Okay, so that's the relatively easy thing where you have finite hypothesis cost. All right. Okay. So and this is a homework question. The Masala is a homework question. I think there's a hint which is actually pretty important, which is you should consider using something about the moment generating function, which will make the math easier. There are two ways to prove it. The other way is that you do discretization plus union bound, and that will give you you'll have a relatively hard time to do that, just because the constant is so hard to make. Like you can work out a similar bound, but just a little bit messy. The moment generating function is really cool. The proof is actually pretty short if you use the right way. You use it in the right way. Okay, so I guess let me just briefly give a quick overview of what we're gonna do next, so that you kind of appreciate why I'm setting up the things here. So the next thing is that what if Q Q is not finite. What do we do? Right. So, and our answer would be that you do some discretization and plus union bound. So you have so basically you have some epsilon cover stuff, and then you have a union bound. Okay, or maybe I should say I have discretization to reduce to the finite case. That's basically the idea. And you probably have seen this idea before, right? Like you have seen it, right, in the third lecture, maybe, when we talk about infinite hypothesis class. But here the difference is that here you are discretizing the output space, the set Q, which is a set of n-dimensional vectors. So before you are discretizing the parameter space, you have a d-dimensional parameter space, you discretize that. But here you are doing a more, in some sense, fundamental discretization, because anyway, the parameters, as I argued, is probably not the most important thing, right? What's really important is that what's the functionality of this family of functions. So now you are discretizing in the right space, in a more fundamental space. This is the space of the outputs. So what we're going to do is we're going to discuss a few techniques to discretize this Q and what kind of like discretization you really need, so on and so forth. So and there's actually some kind of like a pretty deep theorem which is called the chaining, like the Dudley chaining theorem, which actually let you to discretize in a nested way. You have a hierarchical discretization so that you can have the best discretization. So this is something beyond what we have done before. Even you don't care about the difference between the output space and parameter space. Here you can discretize in a much more efficient fashion. So that's what we're going to do next, and then we're going to use this for the multi-layer network. Okay, sounds good. I think that's all for today.